Hi, pre-calculus students. Welcome to section 3.5, last section of chapter 3. It's a short one, but good one. We're going to be solving exponential equations using inverse operations of logarithms. And we're also going to be applying logarithmic functions because they are so important on their own. So hopefully you received notes in your hand on 3.5 to fill in. They are also on Schoology to fill in and filled out. If you didn't get them in your hand though, no worries, because as we go along, you could still, there's not much typing on this. You could easily do this on notebook paper if you don't have a printer or something like that. So we are going to be looking at exponential functions, right? Where you have a starting amount. So in this position, there is some constant multiplying this base of E, because we're going to be talking about natural growth and decay here. We don't just call it an A. It could be a P. It could be an N. But any of these terms that are in that starting position and are multiplying the base, those are the starting amounts. We can call it any letter we want. Okay. Next, we have E because we have a natural situation or have emulated a natural situation. B would be your rate, right? We have called that the rate here. We have called it K here. Again, it doesn't matter what we call it. It is, every single one is the rate. If your rate is greater than 0, that means you're going to see growth from your initial amount. If your B is negative, meaning that it's less than 0, you're going to see decay from your initial amount. Okay, and so let's go on to number 2. On number 2, I may have to wander and do some work in this area and then erase, because they ask you 2 questions. First, they ask you if interest is compounded continuously and you deposit $750, right? There's your starting amount at 10.5%. That is your rate, 10.5%, right? Or 0.105, right? As a decimal. They want to know first, how long will it take? They're asking you time to double your money. So they want this output to be double. So this is the first part in A, and then we'll do B. So notice that if you want to double your money and you started with 750, that means your output would be 1,500. And they want to know when that'll happen. So we have E to the 0.105 T. Here we go. Input, original 750, we want to double it. Here's our rate, and we want to know how long that'll take to happen. We will divide both sides by 750 to isolate the base so that we can take the natural log. Of course, we have 2 on the left. We doubled it. E to the 0.105 T. Here we go. We can now, just like in section 3.4, take the natural log of both sides. And we have the natural log of 2 equals the natural log of E cancels 0.105 T. And to solve for the time, we'll divide by 0.105. And that will give us the time in years. Let's take a look. So I'll put that on the calculator. So as it turns out, anytime you want to double your money with continuous compounding, won't it always be the natural log of 2? Won't you always divide by the rate, no matter what the rate is? So that's a quick way to figure out how long it'll take to double your money. Natural log of 2 divided by the rate that you've been given. So let's throw that in. That's the natural log of 2 divided by 0.105. That will take 6.601 years. There we go. Take a good look at that. I just decided to erase it and then do B, because then on B, the question is, how much money will you have after 10 years? All right, so get a good look at A. We're going to erase. Let's do B. How much money will you have after 10 years? So they're asking you for the output amount. You started with 750. Continuous compounding, there's our E. 0.105 is our rate, and our time they told us is 10 years. So notice all we have to do is run this through the calculator. We don't need to take the natural log of anything. I can put that in the calculator, right? I'm not trying to solve for a variable that's an exponent. So 750 times e to the 0.105 times 10. Notice it'll definitely be more than 1500 because it was only 6.6 years to double and we have 10 years. That comes out to $2,143.24. Awesome. Okay, next, carbon-14 has a half-life of 5,715 years. So as you probably learned, carbon-14 is used in fossil dating, right? And so what it means is if you found a mass of carbon-14 and went and saw that mass 5,715 years later, there it would be half the mass left, is what that means. Okay. Let's see. So let's say that you start with 6.5 grams. How much remains after 1,000 years? Now, what they don't tell you on the half-life problems, and a couple of the other ones may be population. So make a note at the top of your homework. When you are asked for half-life, no matter the question they ask you, you have to have K first. And they don't say it. So you just feel lost. You need K first, and then you can answer their question. Okay, so here we go. Let's see. We started out, here's our starting amount, right? That always starts 6.5 E. Now the K, I am trying to find the K, right? And the time that's going by is 5,715 years. So what goes here? So what goes here is this time matches this output. This time, 5,750 years, will result in half of the 6.5 grams being left. So the amount that goes with these years is 3.25. Right now, I have to isolate the base to solve for K. So I'm going to divide both sides by 6.5. Now, of course, I'm going to have a 0.5 on the left, right? Because it's half of it, right? And e to the K, 5,715. Okay, now here's something I want to talk about real quick. If you have been given half-life years, but not an initial amount, you don't need it. Please don't think that you don't have enough. Here's what I'm saying. Let's say they gave me a half-life of 5,715 years, and they wanted me to find K. Okay. And they didn't give me any starting amount. It's okay. Because isn't it true, no matter what's under here, it's one mass. Whether it's 6.5 grams, 1,000 pounds, or 2.628 ounces, after the half-life years goes by, I'm always going to have half left. So if they ask you, they give you half-life and they want K and no starting amount, you just put a 1 here for the starting amount. No matter what, you have one mass. And here you put a half, because no matter what, you have half of it left with these many years. Okay, that's an important point to make. Put it at the top of your homework too. Okay. Now I can take the natural log of both sides. And I have the natural log of 0.5 equals, natural log of E cancels, 5,715 K, and I'll divide by that. So notice then is whenever you want the K and you have the half-life years, won't it always be the natural log of 0.5? Because it's half-life. Won't you always be dividing by the years that you've been given? Now notice this is going to be a very small number. So let's get this on the calculator. The natural log of 0.5 divided by 5,715. This is a very small number. Here's what my calculator gave me. It gave me a negative 1.213 e to the negative 4. Okay, that's scientific notation. Here's how I'm going to write it. This negative 4 means I'm going to move the decimal 4 times to the left. So I'm going to go over the -1 and it's going to create 3 more places where I'm going to put zeros, okay? So my K then is -0.0001234,121. You can include the 3 also if you want, but for half-life, your K is going to be negative because it's decaying. It's going to be very small because it takes many, many years for many elements to decay. So you're going to have a very small negative number for K, and you need to go 3 significant digits past the zeros. Okay, so here's what I'm going to do. I'm going to put the K in right here. And put the time. Okay, so I'm going to erase this. I now have the K for this particular element. Okay, so here's what I have. They actually asked me for, with never telling me I needed K, and we started out with 6.5. Let's see, they have asked me how much remains after 1,000 years. I didn't realize I had it right on the board. How much remains after 1,000 years? Okay, so I have the output. I started with 6.5. I have e to the -0.000121, and the time is 1,000 years. Notice there's going to be a lot left. It only loses half after 5,700 years. So after 1,000 years, most of it's going to be left, right? So there's not going to be a lot gone. Again, notice I don't need to take the natural log. I'm not solving for an exponent. This I can just put in the calculator. So that's a -0.123121 times 1,000. There we go. So there's still 5.759 grams left, as we expected, right? There's still a lot left. Let's take a look at number 4 on your notes. What if they want you to write an exponential equation and they give you a graph with 2 points? Okay, so this wasn't on, it's on the filled in notes, but it's not on your note sheet. So you need to make this little graph right here, right? Now, there's a couple ways to go on this. Without a doubt, you have been given a starting point here. If you think of it as zero, it is time. At a time of 0, the starting amount is 1/2, right? Later, after 4 hours, the amount is 5. So what you would always do is put in your starting amount first. You could literally just put a half right in there because that's what the A is. Or just to show you that the A is 1/2, let's go ahead and put this in. I'm going to put a 0 for X and a 1/2 for Y, and just show you that the starting amount will still be 1/2. So 1/2 equals A times E, and then my X is 0. Notice that E to the 0 is 1, and it's again, it says right there that my A is 1/2. So you don't have to do any real math. If you see a point that is obviously at time 0 starting, then you can just put your 1/2 in there. Now I need B. I need the rate so that I have an equation where for any X, when I put it in, I can get the Y out, which means I need that rate right there. What do? I use the second point. Here's my X and here's my Y. So 5 equals, you know what? I'm going to write this 1/2 as 0.5. E to the B and times 4. Here we go. I'll divide both sides by 0.5, right? So 5 divided by 1/2 is 10 equals E to the 4B. Natural log of both sides, trying to solve for a variable in the exponent. I get the natural log of 10 is 4B, and I'll divide by 4. And I'll get my B as a decimal, the natural log of 10 divided by 4, and then I'm done. natural log of 10 divided by 4.576. There we go. And I am done. Here is my equation. 1/2 times e to the 0.576x. And for any x I put in now, I could get a y out. Last problem, number 5. Let's say that the value, they're talking about the value of a painting. Isn't it crazy how much value can be in paintings? Let's say the starting value, this is 10, but it's in millions. 10 is $10 million, right? It's like the value of the painting is growing naturally, right? And they're telling us that at a time of 0, which is the year 2000, that the painting, the starting amount was $10 million. So what they tell us later is that in 2008, the painting was valued at 65 million. Isn't that crazy? But it does happen. So they want K, and they want us to predict the value in 2014. So the first thing we're going to do is we're going to put this point in, right? At a time of 8, right, 2008, the output, the value is 65 million. So I'm going to put 65 for the value equals 10 times E. And this is going to be 8. And I'm trying to find the K. Okay, let's divide both sides by 10. And I get 6.5 equals E to the 8K. Natural log of both sides, right? The natural log of 6.5 equals 8K. And we'll divide both sides by 8. Probably by this point, you're seeing a lot of the math is actually the same, right? So the natural log of 6.5 divided by 8. 0.234. Notice that's positive, so of course that's because the value is growing. Okay. Now they want us to predict, so that's our K. So if you don't mind, since we already have this done, just going to come on over to the left and answer their next question. So they asked us to find K, and we did. Okay. Now they want to know. Here's my new equation. My value is 10 times E. I found that the rate is 0.234 times the time. And so they want to know what will the painting be, its value be in 2014. Notice that is a time of 14. And I want the output, the value at that time. So the value equals 10 times E to the 0.234 times 14. Again, notice I am not solving for a variable in the exponent. I can just put this in the calculator. 10e 0.234 times 14. That painting is worth 264,697. Oh, trying to read my calculator right. 696, about $819 million. Isn't that crazy? But it really does happen. I think it would be crazy to have enough money to buy it, right? So anyway, thank you for doing the last section of chapter 3 with me. Have a great day.